Hello. For this assignment, I wanted to use the Movie Lens dataset. I wanted to use the Movie Lens dataset because I personally really enjoy watching movies, and I wanted to see the Movie Lens recommender system and see if there's any potential issues in the fairness, particularly between what movies it chooses to potentially or give potential ratings for males and females. So, if you don't know, the Movie Lens dataset has widespread use as a recommendation system search, and it is used to study fairness issues. So, the way that this dataset was created, or from what I've read online, it is a collection of movie ratings provided by users. It was created and maintained by the Group Lens group at the University of Minnesota. And for this particular one, I will be using 1 million datas. It sounds like a lot, but it's really not. So here is the README file from the dataset that I downloaded. They contain 1 million anonymous ratings of approximately 3,900 movies made by roughly 6,000 users. So let's jump into the code. So the way I broke the code down was into definitions, just so I can go over each of the parts properly. For the first one, I'll just be loading the Movie Lens dataset in. So I already imported it here, as you can see. We'll import each of the 3 data sets, the ratings, users, and movies. Then we'll appropriately label those also. So the README provides the labels for this. It is right here. And also there are some other interesting things that we can look through in this data set. So for now, I appropriately label each of these different datas. I then decided to do a binary labelings for anything that is 4 stars or over, as generally those are good movies, and I feel like most people watch movies that are 4 to 5 stars. Generally, you might watch some 3-star movies, but maybe I'm very snobby in what I choose to watch, but I feel like anything under 4 is a little bit suspect. So, right now, we will merge the datasets. Then we'll extract genre as a feature. And we'll currently separate them as in this dataset, everything is meshed together, which does not allow for clean analysis. Okay. And then for the code, we will calculate the accuracy metrics, MSE, MAE, TPR, and FPR. One of the other things too that will be a requirement for this is all the inputs will need to be trained. So let us get our MP arrays in. We will also check for any missing data, and if it is missing, we will filter it out. But I don't really think any missing data was found. It's just a good error check to have, though. We will have our regression metrics, the mean squared error, mean absolute error. And now we will also do classification metrics if our predictions are binary. We'll have one for the true positive rate and one for the false positive rate. And if those features are there, we'll indicate MSE, MAE, accuracy, true positive rate, and false positive rate. If not, we'll just indicate the MSE and MAE. Next, I wanted to have one that specifically calculated the fairness metrics of it. So one is accuracy, and this one is fairness. So again, we'll convert the inputs to an NumPy array just to make using it a bit easier for me. Then we will get the overall metrics, the prevalence and parity, all like that. We'll calculate the metrics for each of the groups. We will filter by group. We will skip if the group is empty. Then here, I just decided to put metrics which we used from modules 1 and 2. I think that it's quite a bit. It's excessive, but for this, I think it's fine to see all of them. I think it's kind of fun also. Lets me do a bit more analysis. So for that, I chose the prevalence, parity, accuracy, TPR, FPR, all the good stuff. Then we'll return the overall metrics, or the group metrics. Finally, I'm going to concatenate all those definitions or methods into one, which is right here. So first, for this one, we'll load our data. And for this, you'll see throughout the code, it'll be a lot of print statements. It definitely might feel excessive, but I think for the presentation, I normally don't do this, but just for the presentation, I think it's fun to look at all of it, and it'll give you a much better picture of everything. So for that, I printed the shape just so you can see it, the number of users, movies, and then I think the gender distribution will be kind of cool to look at too. So for the results for that, spoiler alert, I think it's around like 75 male, 25 female, which is quite a discrepancy. I was a little surprised by that, to be honest, but maybe I shouldn't be. So now we'll use movie genres as features to predict rating, and then in our genre column, we'll exclude these. Sorry, I meant exclude anything that's not in these. My apologies. So for this one, I also wanted to add gender as another feature. In the code, this is essentially what I do. I also create the gender binary feature. I then do linear regression to predict the actual ratings, and then I do a classification task to predict the high and low ratings. So here we'll see the model trained using linear regression. We'll fit the data, or the model, I mean. Here we'll train the classification model, fit it, all standard stuff. It's all stuff that we've done before. Make predictions, and then calculate the regression metrics. Next, we will calculate the classification metrics. All very standard stuff. Nothing I've done so far has been too crazy. It's a lot. It's excessive, but I think it's fun to look at. Now we'll get the sensitive attributes for our gender, the test sets. We'll calculate the fairness metrics by gender for classification. Then next we'll calculate the regression metrics by gender. Some more print statements, just to print out more data, the prevalence and demographic parity. Next we'll print out the fairness metrics by gender. Calculate the disparities using the data sets. Print the regression metrics by gender. I think, honestly, most of this code is very straightforward and explanatory. I don't know if I needed to go into why or how I'm doing it, but I think it's very simple. Next, we'll calculate the regression disparity. And then finally, I have a lot of metrics and a lot of stuff that I want to see, a lot of variables. So I include that in the return. So for here, I will then basically just run this, which essentially just runs these three definitions. Like I said, it just concatenates it. Then, when I wanted to print these out, I ran into a couple issues when I wanted to print out data. So I basically just made some structures and had some of the data points which I wanted to look at more specifically. These were chosen basically again from Module 1 and Module 2. I used a lot of the same things that we looked at there in here. I had one for the regression matrix, the classification matrix, and the fairness metrics. Basically, it's just, a lot of parsing through the results, getting to stuff that I want to display, labeling it properly. Again, very excessive, but I think it's fun to look at. Finally, I'll print out each of those structs. And for the fun part, here are some other results. So yeah, the gender disparity, again, 75% male, 25% female. This will definitely lead into some errors for the recommender system because you have a pretty huge disparity between males and females. Whether gender actually turns out to be very important, spoiler alert, not really, but we'll have to see. So here, look at the results of our regression matrix. Generally, our prediction model is off by about 1 star, which is honestly pretty solid, I want to say. I don't know how, for me, it might not be, because any movie which is around a 4 is on the cusp of going sub 4, which might not make it that good. But overall, I want to say it's pretty solid. I don't think that's too bad, just by itself. So for our classification metrics, this is what we have. We have a pretty low accuracy rating, around 60%, which, yeah, not too good. Let's see, anything else that's very interesting? here, what we see is actually that the prediction model actually predicts better for female viewers than male viewers. I don't know why that is the case with the lower data set. Maybe I'm trying to think through this one before. I guess the only thing I can think of is maybe the female viewers were more consistent in stuff that they viewed, or they liked a more homogenous set of things, but I doubt it. Here, just going through more of the results. I don't want to waste more time and talk about absolutely everything. So for part 3 of this, discuss which fairness metrics are specifically relevant to your task. I do think that the accuracy parity is pretty important, because I do think that if you are a user that's either male or female, you would want things to be accurate for you regardless of your gender. I think that also for fairness, I do think that in this data set, I assumed that because there was more males, it would have been more favor towards the accuracy for males, but it actually wasn't, which is a little bit surprising. Some of the other, I guess I should go into it. Some of the other fairness metrics that you can look at, which I didn't want to look at, could be potentially age. It could also be what your job is. In this in this data set, they do have an occupation. They do include age. Spoiler alert, because it turns out gender actually wasn't that big. They didn't play that much of a role in the model's predictions. I actually should have probably chosen something else, but I did this initially and I stuck with it all the way through. I think if I wanted to see bigger changes in fairness, I should have chose something else in retrospect, but I think it's also fine to choose something and then be wrong about your predictions. So now for the next part, because our data set is unfair, although very slightly, I wanted to go through parts 4 through 6, which will be the pre-processing, in-processing, and then post-processing, to try to get more favorable outcomes. So for this, I added another function just to prepare our data specifically for pre-processing. So for part 4, for the dataset intervention, I chose to remove the sensitive attribute, which was gender in my case. Why was it chosen? I listed a couple features here. It's very transparent and easy to implement. It directly addresses the concern of models using genders to make decisions. And other methods like reweighing or resampling can introduce additional bias or distort natural distributions of the data, or at least that's what I think they can do. Whether or not that's the case for this particular data set, I didn't run those models. I could be wrong. So we prepare data, prepare variables. So for here, what I want to also show was what the results look like before and after the intervention method. So for each of these parts, I will have a baseline model, and then I'll have the intervention model. Then we can go through the results just to see what the difference is. So for the baseline model, I used like logistic regression. I fit it, trained it. And here I calculated the baseline metrics. We again used the method or the function which I previously made. I then printed out a bunch of the results, a bunch of the metrics. Again, very excessive, but for the sake of the assignment, it's good to see. So here, I actually go into the intervention itself, which is removing that sensitive attribute gender from our features. Basically, very self-explanatory. Remove gender, then remake the data, retrain it on the models, get the predictions for no gender, print out the results which were similar to our baseline for comparison. Next, I wanted to analyze the feature importance for the baseline model. So for this, for our prediction model, I wanted to see how much of a role gender played. I then listed the top 5 features in the baseline model. I next checked where gender ranks in importance. I also wanted to do a comparison for the accuracy and fairness trade-off, because as was discussed in a lot of the lectures, you will have to make a compromise in accuracy to get increased fairness. How much of an accuracy you're giving up and forfeiting is very important, because if you're wildly off on it, then no one's really going to want to use your model. So you do need to actually still maintain a consistent accuracy. So for that, I basically just took the intervention model accuracy score and then subtracted it from the baseline accuracy score. If it's negative, it just means that our baseline model was more accurate, which we should assume that it should be. Next, I saw the TPR disparity change and the FPR disparity change. Print them out. Next, for part 5, for this intervention method, I chose reweighing. Why was this approach chosen? It directly addresses the biases in the training data. It gives more weight to underrepresented group outcome combinations. It preserves the original features and their relationships. And it's been shown effective in various domains, including recommendation systems, particularly movie recommendation systems. I think, from what I've seen online, that is what it said. Don't quote me on it exactly, but because of its widespread use in this domain, I decided to basically use it. And I think also it is pretty simple. Okay, I shouldn't say simple, but it gives you very direct ways to address any biases that you have. Again, same as before, prepare the data, split the data into the baseline set, and then we'll also later have the intervention set. We'll use logistic regression again, get the predictions. I should have mentioned it, but I did the 80-20 split. Very standard. Again, the features basically same as before. Oops. Sorry, there we go. Okay, so next, for the reweighing, I want to compute the weights using reweighing, I also wanted to see basically which type of weights I should use to maintain high accuracy. So for that, we'll start off by calculate group statistics. We'll get the amount of samples, the total amount of males, total amount of females, classification trains, so which are positive. So 1. So if you already forgot, those are any 4 to 5 star movies. 0 or sub 4 star movies. Next, we'll calculate the probabilities for each group outcome combination. And then this will be the expected probabilities if features and labels are independent, which we should assume show. We'll do it for males, females, the positive and negative rates. Next, I wanted to see the expected joint probabilities. So to do that, we'll do the following. We'll then next do the observed joint probabilities. A lot of the stuff standard that we've done and discussed in class. A lot of these formulas were straight from the slides. We'll calculate the weight for each instance. Here, for the weights, we're looking for any males and particularly any ones that had, again, were predicted movie results to be 4 or 5 stars. We'll display the weights for each outcome and the probability and its combinations. Train the model with its instance weights. Calculate metrics for reweighted models. Again, a lot of print statements vary. It's way too much, but still worth it. Here, I wanted to compare feature importance between models. And then I wanted to see the importance for the reweighted one. Check for gender ranks and importance. Yeah, just more stuff listed. For the post-processing, for part 6, I did different thresholds for demographic parity. So why this approach? Again, direct way to address unfairness without retraining the model. It can precisely control the fairness metrics we want to optimize. It's transparent and easy to explain to stakeholders, because if you do want to do model explainability, it being transparent is very important for stakeholders, as we have discussed in class. Other approaches, like the reject method, can be more complex and not as transparent. So here, for the data again, split it, train the model. So for the threshold, I decided to use a standard threshold of 0.5. I didn't play around too much with these. I wanted to just choose something naive, which was just the 0.5. Print out the standard stuff. So for this intervention method, we decided to get male and female probability indices. We'll mask the gender. Here we'll try different thresholds to achieve demographic parity with constraints to avoid trivial solutions. So for part 5, I misspoke about that part. That is my bad. This is actually here where I do it. It's been a very long day. My apologies. So we do exactly that. We go through the male and females. We then try to apply the different thresholds, calculate the positive prediction rates, the disparity, apply constraints to avoid trivial solutions. One of the issues that I ran into initially was the model chose 0.1, I believe, and then it gave me a true positive rate of 1 just because it cheated, like we were discussing in class, and then the way it drew the line to try to fit the model made everything positive. Next, we'll estimate the accuracy of this threshold pair and only accepts solutions with better fairness if accuracy doesn't drop too much, which is around 5%. I think that's pretty reasonable. Next, I wanted to apply the best threshold and create predictions with group-specific thresholds. I calculated the metrics for demographic parity, optimizing predictions, printed stuff that we looked at before, compared accuracy and fairness trade-off, which I think is fun to see. Here is just where I ran all of the intervention methods, parts 4 through 6, loaded the data for each of the methods. Next, I wanted to plot it to give you a bit more of a visual representation of the differences. Again, we did accuracy, disparity for TPR, then parity disparity. Here, I just create the plots. I don't think you're too interested in it. Now for the outcomes, here they are. I'll slowly go through them. So gender as a feature importance ranked 19 out of 19, which I was kind of shocked, but not too much. So for our genres, for the feature importance, film noir documentaries were the highest. Impact on accuracy and fairness, we had a slight change in accuracy. The TPR disparity went down. Next, we have the logical regression baseline metrics, the reweighing. Again, check the outcomes of the feature if it changed. Here, I believe the reason that it's now out of 20 was just it not excluding something like before. I don't think it really made too much of a difference. Then here are our graphs. As we can see, using our different intervention methods are actually barely dropped, but then our TPR went really down. For this last one, I believe that the TPR is very low or near zero just because if you actually look at these numbers, they're already very low. This feature didn't play much of a role in our prediction model. So I don't think the code is wrong. I do believe that the number is just extraordinarily low. Now, particularly for part 7, what types of interventions are most appropriate for your task? I do think that the ones that I chose, in terms of reweighing, removing gender, and doing the post-processing with the group thresholds. I think those are very appropriate. From what I've seen online, those are generally used. I wanted to do something that was generally used and see what the outcomes would be. I do think that other ones could have potential issues, but I didn't test them, so I'm not too sure. Then for part 8, the paper that I decided to go with was the Cameron Calders, and to go over part 8 of it, the main contributions, the paper focusing on addressing distributional discriminations and classification tasks where different groups have unequal access to positive outcomes. It introduces and formalizes the concepts of distributional discrimination, providing a framework for measuring and mitigating it. And then basically the reason why I chose this was I like the formula that I gave for the one I used, and then I want to implement that to evaluate the reweighings and see if there can be any improvements. Although I did say gender did not play much of a role in the weightings, there still actually was in our data an unfairness gap, and there was a bit of a disparity in terms of fairness. So for this part, I am implementing the reweighing with the Cameron Calders. I implement the reweighing algorithm from the paper. Particularly, it was part 3. I wish I could pull it up for you, but I don't have it. I basically just followed the formula that was provided in the paper. So for here, I make things into numpys, arrays for indexing consistently because I ran into issues when I didn't do this. Then I do the protected attribute. I get unique values for the sensitive attributes and class labels. I calculate the weights. This is basically the formula I implemented. I calculate the weights. If the joint count 0, the weight is equal to 0.0 to handle division by 0. So implement the reweighing techniques from the paper. Here, prepare the data for analysis, split the data for training. I apply the reweightings. Basically, this is just the implementation of this method. And again, just like the previous ones, I'll have a baseline model, which I wanted to predict, and I'll then have this, or I should say, the research papers method. I apply the reweighings, train it, evaluate the model, train a baseline model on the original data for comparison, and then I'll evaluate the baseline model. Again, print out a bunch of stuff, which I think is fun to see. And here's the results, where we will compare some to reweighing. I actually went down very slightly. I think this is more than acceptable. And if we see that the TPR disparity went way down, FPR disparity went way down, and then the parity disparity went way down. So this was actually a very good implementation of the model. The outcomes are very good. The lower accuracy score is fine. And also to give you a comparison, so the baseline original data accuracy, this was my data set intervention method I used by removing the gender. And here was the reweighing from the paper. we actually got much better results using theory weighing in terms of TPR disparity, FPR disparity, and purity disparity. I actually did take more of a hit, which, again, I think it's a fine trade-off. So, what did this tell us? So for part 10, it told us that it was much more effective in terms of the intervention method that I used. And I do think that if I'm looking back at it, maybe I did choose the wrong pre-processing one, which was just removing gender, but I think it's fine. So overall, what was very effective and not effective in my task? I do think that most of the intervention methods that I used were effective, as can be seen here. The most effective does appear to be the post-processing, but again, looking at the numbers, you might think, wow, this is huge, but the numbers are so small that it really doesn't matter, to be honest. Plus, looking at the rankings and the changes, I do think that gender didn't play that big of a role for the recommendation system. I do think that for fairness, as can be seen, that we did make the model more fair. We did reduce the accuracy a bit. Overall, what could be another sensitive attribute, which I would look at, I might honestly look at age. I think that one probably might have had the highest outcome, looking back at it now, but can't do much about that. Anyways, that is a presentation. It is very long, but I hope you enjoyed it.